Hello GATE aspirants. Welcome to part 12 of GATE Thermal and Statistical Physics series. Question number 13. For a finite system of fermions where the density of states increases with energy, the chemical potential is option A decreases with temperature, option B increases with temperature, does not vary with temperature, corresponds to the energy where the occupation probability is 0.5. Now the Fermi function for fermions is 1 upon e raised to E minus EF, where EF is Fermi energy, upon kT plus 1. So this is Fermi function, where this EF is Fermi energy, and at 0 Kelvin, this Fermi function is equal to chemical potential. Now this chemical potential is the potential at which the occupation probability is 0.5. So option D is correct. This function looks like this: Fermi energy versus energy. So this will look like this when temperature is equal to 0 Kelvin, and this is 1 and this point corresponds to 0.5. So that is half of it. And as the temperature increases, the graph, it looks like this. This is for temperature greater than 0 Kelvin. And as we increase temperature, this point never shifts. So as we increase temperature, this mu, it will also depend on temperature, and this mu is equal to EF, which is equal to EF naught. EF naught is value of Fermi energy at 0 temperature, 1 minus 1 by 12, and here we have Kb upon E F naught square. So from here we can see if temperature increases, then mu decreases. So it decreases with temperature. So option A is also correct. So here A and D are correct. Next question. Consider a system of 3 distinguishable particles having spin s is equal to half and sz is equal to plus minus half, with corresponding magnetic moments mu z is equal to plus minus mu. When the system is placed in an external magnetic field H pointing along the z-axis, the total energy of the system is mu h. Let x be the state where the first spin has sz is equal to half. The probability of having the state x and the mean magnetic moment of the system in the state x is. Now we have particles whose spin can be plus half and minus half, and there are 3 such particles. So if all of them are having spin up, then that means plus plus plus. So total momentum will be 3 into mu, and corresponding energy will be minus 3 mu h. If any one of them is negative, then this will be plus plus minus minus. So plus minus plus minus plus plus. Here the total moment will be mu and corresponding energy will be minus mu h. If 2 of them are negative, then this will be plus minus minus, minus plus minus, and minus minus plus, and corresponding momentum will be minus mu and energy will be mu h. And if all of them are negative, then it will be minus 3 mu and total energy will be 3 mu h. Now in the question it is given that the total energy is mu h. So this is the part that we are dealing with, out of which this one, first one, in that case sz, first spin, is half, it is plus half. So probability of getting x will be, these are total 3 combinations possible, so 1 by 3. So probability is 1 by 3. And here total momentum is minus mu, so the momentum of that one particle, it will be minus mu by 3. So here option A is correct, 1 by 3 and minus 1 by 3 mu. Next question. Consider a single one-dimensional harmonic oscillator of angular frequency omega in equilibrium at temperature T is equal to Kb beta inverse. The states of the harmonic oscillator are all non-degenerate, having energy En is equal to n plus half h cross omega with equal probability, where n is the quantum number. The Helmholtz free energy of the oscillator is, here energies are given, En is equal to n plus half h cut omega. So this will be half h cut omega, then 3 by 2 h cut omega, 5 by 2 h cut omega, and so on. These are the energies. Now partition function z is equal to summation over I and e is to beta into Er. So here it will be summation of all these terms. So here I can write Z is equal to summation over I, then we have e raised to, and here I can write beta into, so basically it is summation of all this, so let me write it in that form. This will be e raised to minus beta h cut omega by 2, next term is e raised to minus beta 3 h cut omega by 2 plus e raised to minus beta 5 h cut omega by 2 and so on. Here we can take this e raised to minus beta h cut omega by 2 common, so in bracket we have e raised to, and here half omega we have taken common, so this will be e raised to minus beta h cut omega plus e raised to minus 2 beta h cut omega and so on, and this is geometric series and we are taking summation up to infinity. So e raised to minus beta h cut omega by 2, and this is equal to first term upon 1 minus r, where r is common ratio, and here common ratio is e raised to minus beta h cut omega. So this is Z, partition function is Z. Now Helmholtz free energy F is equal to minus of beta inverse into ln of Z. So this will be minus of beta inverse and ln of this term. So ln of this, so this will be, we can take ln of e raised to minus beta h cut omega by 2 upon 1 minus e raised to minus beta h cut omega. So first term is, here first term will be ln of e raised to, so that will cancel out, so it will be minus of beta h cut omega by 2 and then minus of ln and this denominator term. So this is equal to, F is equal to minus minus, it will become plus, beta inverse into b is 1, so first term is h cut omega by 2, then minus minus plus beta inverse, and then we have ln of 1 minus e raised to minus beta h cut omega. So here option D is correct. Next question. A system of two atoms can be in three quantum states having energies 0, E and 2E. The system is in equilibrium at temperature T is equal to Kb beta inverse. Match the following statistics with the partition function. Now first is classical distinguishable particles. So here energies are 0, E and 2E. So let us consider two particles A and B because they are distinguishable particles. And consider energy levels 2E, E and 0. So these are the energy levels. Now these are classical particles, so two can be in one state, so AB, AB, AB. These are three possible combinations. Or we can consider AB or BA, or here AB, BA, or AB and BA. So these are the possible combinations. Now let us calculate energies in all these cases. Here energy will be 0, here it will be 2E, then here it will be 4E, E plus 0 E, E, then 2E plus E, that is 3E, 3E, then we have 2E, 2E. These are the energies. So now Z is equal to simply summation over e raised to beta EI. Now here it is e raised to 0. So first term is 1. Then we have first we have two terms for E. So this will be 2 into e raised to minus beta E. Then for 2E we have 3 terms. So plus 3 into e raised to minus beta 2E, beta 3E. Sorry, 2E2. Then we have for 3E 2 terms. So this will be 2 into e raised to minus beta 3E, and lastly 1 term. So e raised to minus beta 4E. So this is for classically differentiable particles. So here CD is equal to 3. So CD is 3. So that means option C is correct. We can also check for others. So we have next one is C, and that is classical particles, indistinguishable particles. So for those, this Z1 is equal to simply Z upon, these are two particles. So that means this AB are not differentiable. So those particles will be simply AA, and they are classical particles. So just we have to remove this. That means AB and BA will be same thing. So divide by n factorial. Here we have n is equal to 2. So divide by 2 factorial. So that means this Z will be dividing this entire equation by 2. So this Z1 will be simply division of this by 2. So that means that will be Z4. So here Z will be 1 by 2 plus e raised to minus beta e plus 3 by 2 e raised to minus 2 beta e plus e raised to minus 3 beta e plus 1 by 2 e raised to minus 4 beta e. So C1 is equal to Z4. Then we have third case, that is Fermi-Dirac. Now Fermi-Dirac means these are fermions now. So we have three energy levels 0, E and 2A, and these two particles, they are fermions now. So that will be A and A, and only one particle will be in one state. So next is Fermi-Dirac, and that is AA. We have three states 2E, E and 0. So this will be, if one particle is in 2E state, then second will be in E state, E and 0, or this. These are the possible combinations. So corresponding Z will be summation of all these. So Z is equal to e raised to minus beta e plus e raised to minus 3 beta e, because here we have to add those energies. So here it will be 3e, here it will be e, and here it will be 2e, and plus e raised to minus 2 beta e. So just add those energies. So this will be first one. So Ft is 0. And then last we have Bose-Einstein. So here we have two particles. Those are AA, and they are bosons. So single level can contain more than one particle. So 2E, E and 0. So this will be AA, AA, AA. Then we have AA, AA and AA. These are the possible combinations. So here total energy is 2E, E, 0. Then we have 3E, E and 2E. So Z is equal to, first is this 0. So that is 1 plus E terms, we have 2 E terms. So this will be here we have two particles, so this will be 2E here, and here we have two particles, so this will be 4E here. Okay, so we have one term E term, so this will be e raised to beta e. Then we have two 2E terms, so 2 into e raised to minus 2 beta e plus e raised to minus 3 beta e, and this lastly e raised to minus 4 beta e. So here BE is Z2. So option C is correct. So these were all the questions from GATE 2021 paper. If you like this video, please give it a thumbs up and subscribe to my channel for more videos. Keep learning.